line diagram, the UDL which is shorter than span. Let me go to the class. So for determinate structures, so here is a simply supported beam given of a span of 20 meters, and you need to calculate the ILD at the section X, so which is a 8 meters from left and 12 meters from right, and here the influence line rolling load is an UDL which is shorter than span. I'm writing here it's an UDL, so it's of intensity 6 meters and distance 6 meters and intensity it's 20 kilonewton per meter. So we need to find it out. So this is a question. So a simply supported beam of X point, you need to measure the load positions at X. You need to find out all the responses such as the shear force, bending moment, the maximum shear force and maximum bending moment. So let us calculate it. And we know what are the ILD diagrams for calculating the shear responses and the bending moment responses. Now we will look after one. So I am calculating the shear force responses. You know that the shear force responses is first is the negative and the next one is the positive response, and this intensity is X by L and this intensity is L minus X by L. So there are two cases. Since this is a rolling loads, we need to find out the cases. So this is the X point. So let it be the first case is, so since it is a UDL, you need to designate the UDL. So this is the UDL. This point is called as the head of UDL and this point is called as the tail of the UDL. Tail of UDL. So the first condition, keeping the head point in X, so that I can plot like this. See, this is 8 meters, so this is 6 meter. So I am keeping the head at X point. So that is the condition. Right. Now we will find it out. So then after keeping that, you can see the intensity will be here. So this is the negative shear force. So I am plotting only this force. So we will find out what is this X by L. I am having a calculator. So the X is 8. So X is 8 meter and L is the total length which is 20 meters. So which is X by L. So which is 0.4. So this intensity is 0.4. I am plotting just the 0.4 alone. So this is 0.4 and this is 8 meters. So this intensity, we need to find out this intensity since this is the tail of UDL. So we need to find it out. So how can we find this intensity? So we will find this intensity. See, for 8 meters, this is 0.4. We know that. So this is 6 meter and the left of distance is 2 meters. So by using the triangulation laws, so for 8 meter, it is 0.4. Then for 2 meter, what is the intensity? So 0.4 into 2 divided by 8. So the value is 0.1. So the intensity is 0.1. So now we will calculate what is the shear force, negative shear force as per the intensity applications. So you need to find out the area. Since it is a trapezoidal, so we know what is the area? A plus B divided by 2 into H. That is the area. So the area formula is A plus B by 2 into the distance. So here A is 0.4 plus B is 0.1 divided by 2 into the distance. Distance is 6 meter. So what is the value? So which is 1.5. So the intensity or of shear force. Shear force is this area into load or the intensity. So this area is 1.5 and the load given is 20 kilonewton per meter. So 1.5 into 20, so which is 30. So that is the shear force. Have you got it? So this is the negative shear force. So we have calculated on the negative intensity. This is negative shear. Next we need to find out the positive shear. For positive shear, keep the tail end at the x distance. Got it? For the positive shear, we need to keep the tail end at the x distance. For I'm suppose I'm keeping here. So this is the thing. So I'm segregating the positive shear and I'm plotting. So this distance is 12 meter and the UDL has been placed here at the tail point. So the tail intensity, this distance is 6 meter. So and this distance is 6 meter. So this intensity we need to find it out. L minus x by L. So L is 20 minus x divided by L. So this is 0.6. So we can find out this intensity. What is this intensity? This intensity is for 12 meters, it is 0.6. So then for 6 meters, what is the value? So 0.6 into 6 divided by 12. The value is 0.3. Okay, we got the base. So this is 0.3. So we need to calculate the area. So what is the area formula? So the area is equal to A plus B by 2. So A plus B divided by 2 into the intensity is 6 meter. So into 6. So what do you get? 0.6 plus 0.3 divided by 2 into 6. So obviously the value is 2.7. So now superimpose the loads. So positive shear force is area into load intensity. Load intensity is 20. So which is 2.7 into 20. So which is 54. Right? So this is how we are calculating the intensities or the shear force, positive and the negative shear force. Next we will calculate the bending moment. So let us now calculate the bending moment for this static determinate structure. So for the same condition I wrote, and I also made the ILD for bending moment profile, which is x into L minus x by L with this value, the intensity. So which is 4.8. So now I need to superimpose the load for getting the maximum bending moment, but I don't know where exactly the maximum bending moment lies. So for that condition, I'm keeping the load, I'm superimposing the load over the section point x such that this distance is x and this distance is 6 minus x, so that the overall distance is 6 meters. So now I'm making a relation, you just note it down. So A1x, so A1x by AX will be equal to B1x by BX. So on this equation, you know what is the value of AX and BX? I'm rewriting this as A1x as x, see, and AX as 8 meter, and B1x as 6 minus x, and BX as 12. Right? So I'm cross multiplying the factors, which will be 12x, which will be equal to 8 into 6 minus x. So which is 12x is equal to 48 minus 8x. So which can be even written as 12x plus 8x, which is equal to 48. So which gives you 20x is equal to 48. Thereby x is equal to 48 divided by 20. So which is 2.4 meters. So this is 2.4 meter. So what will be that value? So which is 6 minus 2.4. So which is 3.6. So now superimpose the load here. So such that this is x. So I'm going to make the intensity value. I'm going to superimpose the load here such that from x the left side value will be 2.4 and from x the right side value will be 3.6. So we need to take the area. Before taking the area, let me find out the value. So this is 4.8 and this distance is 12 meters and this distance is 8 meter. So I'm finding this intensity. We know that for 12 meters, same principle, for 12 meters it is 4.8 Then for what is this distance? Which is 12 minus 3.6 minus 3.6, which is 8.4. So which is 8.4. What is the intensity? Into 4.8 divided by 12. So which is 3.36. So the intensity is 3.36. Such that same way I am also calculating the intensity for this profile. So for 8 meters it is 4.8, and for 8 minus 2.4, so what is it? 5.6. So this distance is 5.6. So for 5.6 meters of profile, what is the value? So into 4.8 divided by 8, so the value is 3.36. So it's similar. So now we'll find out the area. So for breaking out this area, I'll simply take this as area 1 and take this as area 2. So the area 1 is base, so which is 3.36 plus the height is 4, a plus b, so 4.8 by 2 into the distance is 2.4, so which is 3.36 plus 4.8 divided by 2 into 2.4, so which is 9.8, and that of A2 is same, 3.36 plus 4.8 divided by 2 into the distance is 3.6. So 3.36 plus 4.8 divided by 2 into 3.6. So which is 14.68 or 14.7. So the A1 plus the A2. So that is the total area. So 14.7 plus 9.8. So which is 24.5. So that is the area. So now we can superimpose the load over this area. So this is the bending moment is area into the load. So which is area is 24.5 into the load is 20. So which is 490 kilonewton meter. Next we'll find out the maximum shear force and absolute maximum bending moment. Now we are going to calculate the maximum positive, maximum negative shear force and absolute maximum bending moment. So we know that maximum positive shear force occurs at the left support and the corresponding ILD is like this. So for 20 meter of span, the intensity is 1. So now I am superimposing the load here. So which is 20 of span x 6 meters. So we need to find the intensity. We know the value for 20 meters it's 1. Then for this is 6 and this one is 14. So for 14 meters, what is the value? 14 divided by 20. So the value is 0.7. So this is 0.7, and you know what is the area. You know how to calculate the area. So the area will be 1 plus 0.7 by 2. I am directly calculating the shear force. You know the shear force is area into load intensity. So 0.7 into this distance, which is 6 into the load. Load is 20. So which is 1.7 divided by 2 into 6 into 20. So which is 102 kilonewton. So this is the maximum positive shear force. For the negative shear force, we need to keep the intensity at the right half, as we know. So this is the intensity. You need to find it will be much more same. So which is also 0.7, and this distance will be 1. So the intensity won't change. So therefore the negative shear force maximum will be such that minus 102 kilonewton. That's all. So for now calculating the absolute maximum bending moment, we know in a determinist beam, in a simply supported beam, the maximum bending moment will be at its center. So I am plotting the point as in center, so which is 10 meter on either. Now also I need to keep the 6 meter at the center, so which is 3 meter on either. So this is 3 meter and this is 3 meter. So which will give you the maximum bending moment. And for maximum bending moment, we need to calculate the central intercept also. So which is x into L minus x by L. For this condition, x is 10 and L is 20. So which is 20 minus 10 into 10 divided by 20. So